Good afternoon, everyone. Thanks a lot for coming here. It is my great pleasure today to introduce Pavel Pancheka, who is my good friend, former lab mate, and an excellent programming languages researcher, all in once. He is starting this year at the University of Utah as an assistant professor, and over the past several years, he's been doing a lot of interesting work on formally specifying web page layouts, design, CSS, verifying it, synthesizing web page layouts and design, and generally doing a lot of work on accessibility and usability of web pages viewed from the lens of the programming languages community. So I think it's going to be super interesting. I will pass the torch to Pavel. Here we go.
All right. Thanks, Alex, for that great introduction. Yeah, so as Alex mentioned, I was at UW until a month ago, and now I'm sort of in this in-between state, transitioning over to the University of Utah. Alex was kind enough to schedule a talk in the last couple of days that I'm in Seattle. So, this is the most up-to-date results you could get. I had to figure out how to, where to fit this logo and everything. So, all right, let me tell you about my work. And as Alex mentioned, broadly speaking, it's about how do we think of web pages and web page designs as an object we can explore from a programming languages perspective. So let me actually start immediately with an actual website. So here is a website you might have heard of, at least in the news. This is healthcare.gov. It's America's health insurance marketplace. And healthcare.gov has to do a lot of things to accommodate to users with various disabilities. So let me give you just one example of something it does. Healthcare.gov supports this feature called text zoom. And text zoom is where you can click a button and increase the size of text on the page. And you can imagine how this is helpful to users who have difficulty seeing, right? Because the text is bigger and easier to read. Now, the reason this kind of thing is possible is because web page layouts are basically programs. They take in inputs like the user's preferred font size, like the size of the browser window, like the platform you're operating on, and so on. And the output from this program is the design that you see in the browser. And like any kind of program, these programs too can have bugs. So take a look here in the top right-hand corner of the screen. There's this search bar and search button. And now I'm going to increase the text zoom level and watch what happens to them. As you can see, the search bar left the toolbar it was in, and the search button disappeared entirely. It's actually occluded by this picture of a child. So as you can imagine, this can make it harder to use this website. And this problem affects not just healthcare.gov. It affects all sorts of major websites that we use to understand our finances, to get an education, to manage our health. Problems like these affect a lot of people. Something like 1 in 8 Americans has a disability of some kind. A significant fraction of these, maybe 1/3, maybe 1/4, have a disability that affects how they can use the internet. And not only is it a lot of people that are affected, but it's also important, not just morally, but also legally, to make accommodations for users with disabilities. It's part of, in the United States, the Americans with Disabilities Act. So bugs like these that you see on some of the biggest websites in the US really shouldn't exist, or at least fixing them should be a high priority. Which leads to this mystery. If they shouldn't exist, why were they so easy to find? These were actually the first 4 websites I tried. It was not a hard slide to make. Well, I think the reason these bugs are so common is not a lack of interest by web developers, but actually the process by which we develop websites. You see, today most websites are designed under a manual testing regime. The web developer just looks at what the web page looks like, adds some manually selected set of browser sizes, browsers, platforms, text zoom levels, and so on. And we know that manual testing misses a lot of bugs. That's not a surprise. So researchers have been working on automated testing regimes, where you have heuristic tools that compare, say, a website at 2 different browser sizes, 2 different browsers, and tries to heuristically tell whether or not a problem has occurred. And you can use that to try out a random selection of configurations. And you get much better coverage this way. So this work is great. It's been adopted in industry, and it really does help find and fix some of these bugs. But we know from our experience with general purpose programming that even random automated tests miss some bugs. And given the importance of the problem, we'd like not to do that. So for the last couple of years, what I've been focusing on is catching all of the accessibility bugs in a web page as best we can, going beyond automated testing to build out a verification regime. So when I say verification, what I mean is that I've built a tool called VizAssert, where you can write down a formal specification for what it means for your web page to be accessible. And then we can prove that that specification holds for all of the browser sizes, text zoom levels, browsers, platforms, etc., that your web page needs to support. So in this talk, basically, I'll be telling you about how that tool works and the techniques we've built to make that possible. And broadly speaking, the tool works in 3 steps. First, we start with a formalization step, where we formalize the accessibility property that you want to prove about your web page. And that turns the accessibility property into a set of equations describing which browser configurations, again, browser sizes, text zoom levels, etc., are accessible. Then we solve that set of equations to determine either that they're all accessible or that some aren't, and produce as a counterexample one of these inaccessible browser configurations. So that's the second step of the process. And third, I'll tell you a little bit how we can scale this process up from smaller web pages to bigger and bigger ones so that we can actually attack this problem in the real world. But let me start by telling you a little bit about accessibility. So a modern web page is written in a mix of 3 different programming languages. There's HTML, which defines the content of the page. There's CSS, which defines its appearance, and JavaScript, which defines how it interacts with the user. And for most of this talk, I'll be talking about static web pages with no interaction, so let's ignore JavaScript for now. Now, when you write a web page, when a web developer writes a web page, they have a bunch of goals they're trying to achieve. They want their web page to be beautiful, usable, easy to use on a mobile device, and so on. And the tools that I've been building really are applicable to all of these, to any sort of task where you need to know about the appearance of a web page. But I think some of the challenges and also needs are starkest when we're talking about accessibility. So that's where I'm focusing this talk. Now, what do I mean by accessibility? It's complicated because there are a lot of different kinds of disabilities and a lot of different ways you could plausibly try to accommodate for them. But this task has been taken up by accessibility researchers who've developed a set of guidelines for the most common and useful accommodations for the most common and problematic disabilities. These guidelines cover a range of different things. Some talk about just the size and position of things on your screen. Text should be big enough, it shouldn't overlap, etc. They talk about how to assist users who access the web through screen readers. So these are devices that speak the content of the page for users who are blind. And there's also functionality that your page ought to support, like the text zoom feature that I showed you earlier. So it's quite a diversity of these guidelines, but as you start parsing through them, you realize that there's kind of 2 core principles going on. First, each of these guidelines select particular elements of the page to which they are going to apply. And then they constrain the geometry of those elements, whether that's the size, the position, or the relative position of multiple elements. Now, I know I haven't highlighted any of these functionality guidelines down here, but let's dig into one of those a little bit further. So let's look at this text zoom property. The guideline says that you should be able to zoom text up to 200%, twice the size, while maintaining the same functionality. So for healthcare.gov, what is this functionality that we're talking about? Well, I guess it's searching the page. So we might say that the guideline can really be translated into this behavioral description, which is that the search bar and the search button should be inside the toolbar. So they actually look like buttons in the toolbar for the text zoom level that I've described. And once we've elaborated this guideline, we can see that, again, it includes these core operations of selecting parts of the page and constraining their geometry. And once we have these 2 core operations, we can start to imagine how we turn this into a formal specification. So when I say select particular parts of the page, well, you could do that with a CSS selector. That's a technology familiar to web developers. And when I say geometric constraints, well, we know a bunch of geometric primitives from mathematics that you can apply to do this task. So we can take this behavioral specification and now turn it into a piece of code. And I'll get to you in a moment. And this code in this language I've developed called Visual Logic basically allows you to do these operations, select parts of the page, constrain their geometry, and thus provides a way to formalize an accessibility guideline as something machine readable and understandable. And a benefit here is not just that we have a collection of guidelines that we've written down formally, but also that this process is flexible. Here I've used selectors that are particular to the page in question. Those could be modified for different pages or also different uses. So for example, on healthcare.gov, this search bar and search button only appears on desktop displays. So we can take this guideline and extend it with a width constraint to make sure that it only applies on desktop. Ben?
Yeah, so I guess the inside the toolbar, I mean, there's a higher level assumption that the toolbar is visible. I mean,
yes.
So do you encode that, or how does that show up in your
You could. So, I mean, part of the flexibility provided by Visual Logic is that there are usually lots of ways to encode some general high-level idea. Right, and this is just like programming in general. Anytime you have a high-level idea, there's lots of programs you could write to express it. So here I've chosen to say that they should be inside the toolbar. You could say that they shouldn't be occluded by anything, which is maybe a slightly different goal, right? Like, if they're not occluded, but they're in some weird place, how happy are you with that? Here I didn't specify that they should be on the right-hand side of the toolbar, but of course you could have. Right. The logic is flexible enough to let you do that. Alex?
So, these are all static properties.
Yes.
And I can see behavioral properties being also concerned with dynamics of a page.
Yeah.
What happens when certain events fire.
Yeah, so I'll get back to the question of dynamic web pages. That's something we'd like to do, but as sort of the first few phases of the work haven't touched that. That's a whole separate can of worms.
Right.
Hi. So if I'm a programmer that's going to use this tool, do I start just writing the visual logic, or do I have some other specification language to use?
So right now, we have sort of a large set of pre-written ones, but yeah, they're written in Visual Logic. I think developing higher level languages that are useful for designers is something we'd like to do. I'll sort of talk about that briefly at the end. You can also imagine templates, right? Like here, this and this are web page specific, but the broader idea is not. You can imagine a templatized system as well.
I think it would be nice if you can, say, incorporate into the CSS or HTML as part of the web page.
Yep. You could put that in the HTML and try to specify it that way. Definitely. And there's also questions like there's this language called ARIA, which allows you to annotate parts of the page with semantic information that's useful for accessibility. Semantic information like pop-up or alert. So you can imagine you can make use of those from Visual Logic as well. So you can embed that information if you'd like. All right, so what we've done here is we've gone from an accessibility guideline into some behavioral description and then into a formal specification. And once we have this formal specification, you can see how we can start turning it into equations that describe the semantics of the specification. And what that really means, right, is taking your geometric primitives and turning them into a set of equations or inequalities. And these are going to be equations over the size and position of the various parts of the page. Right, so here, within is going to be some description of the edges of one box being outside the edges of another. So that's where we can turn accessibility guidelines, English language high level, and interpret them and then write them down formally as a specification. So now, given that the specification has meaning in terms of sizes and positions of web page elements, let's talk about where those sizes and positions come from. So the tool that takes a web page and gives you the size and position of the parts of the page is called a web browser. And a web browser takes as input HTML and CSS. And there's also this other input, which is the browser configuration. How big is the browser window? What browser is it? On what device? And user preferences like text zoom level and so on. I've been referring to these two, browser size and text zoom, throughout, but there are dozens and dozens of these, getting more and more obscure over time. So a web browser takes these inputs and it produces a rendering, a picture. But to get that picture, it first has to determine where every part of the page is and how big it is. So it's that intermediate step that we're interested in, where we get the size and position of the elements on the screen. Now, luckily, web browsers exist. There are, lots of them. I suppose, given that this said Microsoft, I should have put Edge at the very left, but so it is. But lots of web browsers exist. Unfortunately, developing a web browser is an enormous amount of work. Every web browser is several million lines of code. They've all been in development for decades at this point. There are dozens of developers working on each of them. And not only do we need a web browser, but we need a special kind of web browser. You see, web browsers work on known sizes and text zoom levels and so on. But in our case, we don't know the browser size and the text zoom level. We're looking for one. So we have a symbolic user configuration. And we need some kind of, I guess, symbolic web browser, which presumably produces a symbolic rendering, a rendering where the size and position of the elements on the page are dependent on these unknown configuration parameters. So the question is, where do you get a symbolic web browser? And the answer is, you got to write one. Now, this is a challenge, first of all, because web browsers, like I just mentioned, are enormous undertakings. But also, the symbolic part is a challenge as well. In PL, we write a lot of symbolic programs. But web browsers are unusual in a few ways. First of all, web browsers are graphical. So we need to find some way of writing down encoding for geometric operations and for reasoning about those geometric primitives. And then also, web browsers, as I mentioned, are really big, significantly larger than the sorts of symbolic programs that we frequently write in programming languages research. So we need to find a way to take account of these two problems and overcome these challenges. So I could be telling you war stories here for a couple of hours, but I'll restrain myself to just one example to give you a sense of the problems that come up and how we approach them. So on the web, there's this feature called floating boxes. Here, the orange blobs are the floating ones, and you can see the text wraps around the floats that are next to it. So how do we describe wrapping around as a mathematical equation? Well, my idea was it's not really the wrapping around that we're interested in. What we're interested in is the region of the page where text is not allowed to go, something I call an exclusion zone. And we're going to need some data structure to represent it. So what operations does this data structure support? Well, the exclusion zone starts off empty. So we're going to need a way to add floating elements to it and update the exclusion zone to show the new understanding of where text is allowed to go. And then once we have an exclusion zone, we need to figure out where the text goes given the shape of the exclusion zone available. So we need to implement these two operations. And the saving grace here is that there is a particular shape that these exclusion zones often have. And this is just due to how the web browser works, which is that this shape is always a set of stair steps up and then a set of stair steps down. And here the down is a single step. So to describe a shape like this, given this constrained geometry, it's sufficient to write down the position of each of the corners of the shape. And so you can imagine doing that kind of like this, where each corner has a x position and also a y position. And we can write down all of these corners together into a set of triples, like so. So this set of triples represents this exclusion zone. And you'll notice this is not the most obvious encoding, which would just be the xy coordinate pairs. There's some tricks you have to put into this to make it efficient. So for example, here I'm duplicating this right-hand edge 3 times in 3 triples. And the reason for that is this way we can compute these operations like add and place in a single pass, walking from low to high y values. And that turns out to be the sort of operation you need in a web browser. So thanks to some encoding tricks like this, we can do these add and these place calls in a single pass. That single pass is important. That means there's O of n equations to solve. And that's going to make the reasoning process for exclusion zones scalable when we give it to a solver. I'll be talking about that in a moment. But before I do that, here I've described that we have this new concept called an exclusion zone, a new data structure to represent it. Web browsers by themselves don't use a data structure like this because they have slightly different constraints. So we need to make sure that the web browser, the symbolic web browser we've written, behaves the same as a real web browser. So here we're helped by the fact that web browser developers care a lot about bugs and about making sure different browsers behave identically. So there's already a large set of standardized tests to make sure that different web browsers have the same behavior. Now these tests are non-automated. They expect a human to sit in front of them and tell you whether or not you passed. But we don't need to pass the tests. We need to do the same on these tests as existing web browsers do. Because existing web browsers are already known to pass the tests. Humans have done that part. So we can apply differential testing to do this validation. And that lets us pass check that we pass thousands and thousands of these conformance tests. Basically, all the conformance tests that apply to the subset of CSS that our browser supports. And I said basically all because there are a few where we found we don't behave the same as existing web browsers. And those are cases where existing web browsers fail those tests. And hopefully they'll fix those. Actually, Firefox and Chrome are currently working on rewriting their layout system from scratch because it's just become impossible to fix the remaining bugs in them and continue iterating and improving it. So that tells you how we can go from an accessibility property on a web page down to a set of equations that take these browser configurations and tell you whether or not that configuration is accessible. So the next step is solving these equations to figure out if all possible browser sizes or whatever are accessible, or whether there's some where you have a problem. So what we'd like to do is pass these equations through some kind of magic box that tells you either that the layout is accessible or gives you a counterexample. And formal methods type people have built a lot of these different magic boxes. And they differ based on the sorts of equations that they operate on. But unfortunately, none operate on the sort of equations produced by my symbolic web browser. So I kind of surveyed the landscape. I picked the closest thing, which was a type of solver called QFLRA. And what those letters stand for, which is quantifier-free linear real arithmetic, you can think of as the limitations on the equations that our solver understands. So when I say real arithmetic, for example, that means it models exact mathematical arithmetic, not the rounding errors that actual browsers run into when they use floating point or fixed point operations. When I say linear arithmetic, that means you cannot multiply unknowns. As you might imagine, multiplication is kind of like this basic operation that browsers do sometimes. And quantifier-free, in a rough sense, basically means you can't have nested loops. You can't model software that has these nested loops. So these are some limitations that we need to overcome.
Well, my question was, in geometry, you have a bunch of nonlinear equations.
Yeah.
So how do you deal with?
Yeah, so in geometry you do, because in geometry you have circles. But on the web, you don't have circles. And that's basically the rough answer to your question, right? This is basically mostly the geometry of rectangles. And you do find some multiplication. Classic examples are percentage widths, right? It's a percentage of something that involves a multiple. Font sizes, which are also often multiples. But mostly we're not dealing with anything but linear equations. And that means that overcoming the inability to multiply is not the major challenge it would be for like a pure geometry library. Other questions?
So all the properties for in this schema are decidable? That's what you're...
Yes.
Okay.
Yes. So they're decidable, and what we basically found, decidability isn't always a requirement. It might not be decidable in theory, but in practice it is. But we found that loosening, especially quantifier-free or linear, usually leads to the solver giving up. And then you don't get any practical value either. All right, so we need to find some way of overcoming these limitations that we get from the solver. So here's how we did some of that. Rounding error. Well, it's true that the solver does not implement an arithmetic with rounding error, but we can simulate rounding error by turning exact equalities into these bounded difference calculations. This is a trick from numerical analysis. So we can get rid of this problem of no rounding error pretty easily. Another challenge is the lack of multiplication. So as I mentioned, there's not that much multiplication, but we need to get rid of kind of all of it. And the trick that we use there is something from compilers called value set analysis. That basically tells you the set of values a variable in your program can take on. So for example, if a here is either 2 or 3, we can replace this multiplication of unknowns with a large case statement around a multiplication of constants. And it turns out that given the structure of a web browser, in our case, we can always do this to one of the two arguments to a multiplication. So, of course, the right-hand side here looks a lot more complicated, but it's something that the solver can deal with significantly more efficiently. So that handles multiplication. The final and biggest challenge, though, is these nested loops. It's kind of worse than it sounds because in a web browser, there's one loop bought and paid for. You have n elements on the page, and if you want to know where all of them are, you got to loop over them. So no nested loops is more like no loops, right? You have to do a bounded amount of work for every element on the page. And that's a pretty tough challenge to meet. So what do we do? Well, I took inspiration from some compiler optimizations, which you normally apply to programs, and found a way to think of them as applying to constraints. And these are optimizations like incrementalization, loop fusion, or loop unrolling. Let me give you an example of how these might apply. So here's one thing a browser has to do. It has to determine how tall a line of text is. And the standard tells you how to do it. You have to find the tallest letter, get its top, subtract from the bottom of the lowest letter. Makes sense. The challenge is the word tallest and lowest. That means you loop over all the characters in a line once you finish placing them in that line. And that means you've got a loop at the end of the line. You're no longer doing a bounded amount of work. So what do you do? Well, you got to replace this loop at the end of the line with some kind of incremental running maximum. You can update that as you step through the line, and then just access that maximum at the end of the line. So that gets rid of this inner loop and removes the problem with nesting here. Something similar but a little more complicated comes up in this browser feature called margins. A margin is an area around a page, around an element, where other elements shouldn't go. So here I've got a blue and an orange rectangle, and I've drawn the margins around those with arrows of the same color. And on the web, these margins, in some but not all cases, are allowed to overlap. And that some but not all cases is kind of the problem. There's a bunch of these finicky rules, but one in particular stands out, which is that margins are allowed to overlap between two elements, even if there's another element in between them, as long as that element has 0 height. Look, guys, I did not write these rules. I found them as they are. The people who write the standard have an official list of mistakes, and this is on them. But the point is, if you want to model what web browsers do, you've got to model what web browsers do. And web browsers do this crazy thing. The reason this particular rule is problematic is because determining which elements have 0 height means recursing over potentially all the other elements on the page. At least you got to look at your preceding siblings. So we again have this inner loop. Every time you place an element with a margin, you might have to loop over the other elements on the page to determine if they have 0 height. So what we do instead is we try to fuse this inner loop with the outer loop that already recurses over all the elements to determine where they're placed. In other words, we're going to interleave this computation of which elements have 0 height with the element by element rendering. So we basically maintain a pointer to the last non-zero element, non-zero height element. And this kind of fusion between the inner and the outer loop again gives us a single loop, no nested loops. Life is good. A final challenge with loops comes up when we have these data structures. So I was talking about exclusion zones earlier, and if you recall, that data structure has an entry for every corner of the exclusion zone. Well, it can be an arbitrary number of corners in the exclusion zone. So this is an arbitrary sized data structure, and if you have an arbitrary sized data structure, you do operations on it with a loop. So what do? The solution here was in some sense loop unrolling. Take the first k iterations of that loop and implement them as straight line code. So if you have up to k corners in the shape, you can do all the operations exactly. Now what about if you have more than k? Well, in that case, we can get a third kind of output from the solver. Not a proof or a counterexample, but an example where the k we chose isn't big enough. So what do we do in this case? Well, in this case, we increment k and we try again. And you can keep doing this. Eventually, you will succeed, because if you have a k as large as the number of elements on the page, you're definitely good. But in practice, this loop stops at 3 or maybe 4. So this is a significant speed up over actually tracking all the elements on the page. OK, so thanks to these various ways of overcoming the solver limitations, we actually have a practical tool for verifying web page layouts. So we tested it on this collection of templates from freewebsitetemplates.com, which, despite the shady name, is a forum where a bunch of professional designers make web pages for other people to use. So I went to this web page. I collected 100 web pages. Of them, 62 used the subset of CSS that we had formalized. So CSS is massive. There's all sorts of weird stuff in there. I'm not going to get to all of it, but I think 62 is decent. Then we combine these 62 web pages with a collection of accessibility properties that we found in places like the Department of Justice legal guidance. Not every property applies to every page, but between these we have several hundred combinations of web page and web page property. And we can run our tool on these. And the results look something like this. You can see that in the vast majority of cases, we verify that the page satisfies the property in question. That's good. In the vast majority of cases where we don't, that's because we find a counterexample that we can then reproduce in an ordinary web browser, verify that there is an accessibility property by checking against the original accessibility guideline. And so we found a real accessibility problem in the page. There's only a small number that either we couldn't reproduce because real browsers don't do this, or maybe Safari does this and we didn't have access to Safari, or it timed out. So that's a fairly small portion of the overall set. So this is pretty good. We now have a practical tool we can apply to real web pages that people other than me wrote. You know, some evaluations are. But these are real world web pages that we can verify real accessibility properties of. So the last thing I want to do is tell you about how we can scale this process up from the relatively smaller web pages I found on freewebsitetemplates.com to bigger and bigger pages in the real world. Because while the tool I've described so far is practical, it is slow. As the number of elements on the page increases, the time to verify it grows nonlinearly. And that makes sense because it's doing equation solving. We know that solving a system of linear equations is n squared or n cubed, I forget. But worse than linear usually. And in particular, the part of this that is slow, the real challenge here is reasoning about how browser rendering works. The rendering algorithm is huge and it's complicated. And reasoning about this is what causes a challenge for the solver. So how do we scale this non-linear process up to large pages? Well, the idea for reasoning about large pages quickly is the insight that every large page is a bunch of small pages glued together. This is a classic trick in programming languages. If we can divide the page into smaller pieces, we can reason about those pieces efficiently, and then hopefully we can find some way of gluing those small pieces back together to learn something useful about the page as a whole. So here's how we do that. Let me look at this hypothetical example page. And I'm going to call the two pieces the template and the component. Now, in a real web page, you're going to have a template with lots and lots of components in it. Those components are themselves going to be templates for subcomponents, and so on and so forth. But here I've got two to keep things simple. Now, the main question is, how do we reason about the component in isolation from the template? And the challenge is that the layout of the component depends on the layout of the template. It might be something as simple as the width that the template allocates for the component. And not only that, the layout of the template depends on the layout of the component. For example, how tall the toolbar is might be relevant to what's going on later in the page. And we do deal with these kinds of interdependent, interrelated components in PL. But also remember that on the web, there aren't modular function boundaries. The web wasn't written to be modular in this way. A web page is just one blob that's interpreted as a whole. So we need some way to reason about the component when the rendering of the template is unknown. And the way we do that is to treat the rendering of that template as part of the configuration or parameters for the rendering of the component, just like the width of the browser might be. And that means that we're basically verifying the component against an arbitrary template that it might be included in. Or more realistically, because arbitrary includes a lot of weird templates, you can set up a precondition on the rendering of the template, like the width that it leaves available, the position of floating elements, and verify the component against all templates that satisfy that precondition. So this allows us to take a component and verify this sort of implication statement about it. And we can apply the same principles to reason about the template independent of the component. So maybe we can do that and prove the precondition about it. So now what we'd like to do is combine these two components and check that all the preconditions are satisfied. There's a final hurdle here, which is, I told you moments ago that reasoning about a whole web page is too slow. I've broken it into pieces, reasoned about them independently, but now that I put them together, I've got a whole web page all over again. So isn't this final checking step going to be just as slow as it was in the past? And the way to fix that problem is to realize that for this final step, we don't need to reason about browser rendering. This step is what we call layout agnostic. We can check that these preconditions are satisfied as a matter of pure logic and derive the overall specification that we're interested in. And because we're not reasoning about rendering, the overall checking process is fast. So thanks to this two-phase thing, where we reason about each component with browser rendering in mind, but the interrelationship of components while ignoring browser rendering, because of these two phases, we get the ability to scale to significantly larger pages. So one part of that is, of course, the problem size. Components are smaller. Since the process is nonlinear, that leads to a speed up. But there's other benefits, too. Since each component is independent, we can do that in parallel, different threads, different machines. And also, since components are now independent of the web page they're located in, we can cache components that reappear in multiple pages. That might seem not particularly plausible, but think about, for example, a sidebar or a heading that appears on every web page on your website. So caching can lead to big speedups there. So thanks to these three factors, we've been able to scale this verification process up orders of magnitude in web page size and orders and orders and orders of magnitude in speed. That really is 1,400x. And we've also been able to work on multiple pages on the same site where, for example, that caching is a big benefit. I don't have it on the slide, but this should be published at OOPSLA this year. All right. So I've now told you about sort of the three steps toward verifying web pages and how this tool that I've built called VizAssert works. So I'd like to take just a few more minutes now to tell you what's coming next in this line of work. See, there's a lot of cool things you can do with the techniques developed so far, but you've all also brought up a variety of limitations that it has that I'd like to get rid of. And so the most obvious one is dealing with dynamic web pages. Let's start with front-end code. You know, on the front end, most web pages have JavaScript these days. And in fact, most even static web pages have pieces created by JavaScript. You know, Facebook might look like a static page when you load it up, but it does a lot of stuff in the background. So how do we verify a web page if we don't even know the contents directly, if it's only created by JavaScript? Well, I think this isn't actually as hard a problem as it seems. What we need to do is take the pieces I've already told you about and apply one special ingredient, which is induction. Induction means that we can take some unknown number of pages plus, a new page, and note that this page has some sort of text template, a new element which has a text template, and prove the same inductive property about this larger collection. And so we can apply induction in two ways here. One is over data structures in JavaScript. If you have to add n posts to your Facebook feed, well, we can iterate over n, induct over it. We can also induct over time. As the user interacts with the page, we can induct over the operations and changes that JavaScript has made to the page. So this is one core ingredient I'm trying to add to this system to make the system handle dynamic web pages. Another thing to think about is backend code. So what I mean by backend, sure.
Well, on the first slide, but induction, in my understanding, is it's not that fully automatic.
It's not. Yeah, so as you get to larger and larger, more and more complicated pages, you are looking at more and more programmer assistance. And so I'll talk briefly about, at the very end of this, we'd like to make this a more automatic process. But, as we know, synthesizing these preconditions or inductive invariants is a hard problem in and of itself. I think there is the hope that the inductive invariants we're looking at are going to be a lot simpler than the sort of inductive invariants you have in programs. And they're going to be geometric, not data structure-y. So it might also be a little more intuitive to work with them. And so that's part of the hope there. Other questions? Cool. So the other sort of dynamic web page I'm interested in is backend code. So what I mean by backend code is that most web pages these days are generated by some code running on a server somewhere, written in something like Python. And actually, when I say written in Python, let me refine that a little bit. It's written in kind of this mixed language, which involves some HTML and CSS templates that are glued together by some kind of Python code. So how do we reason about this mixed language, multimodal program? Well, my idea is that these snippets of HTML and CSS, they sound a lot like the components that I was talking about earlier. And we already know how to reason about these components in isolation to go from a component to some kind of specification. So now what we need to do is check that these preconditions and postconditions are satisfied. And to do that, we reason about the control flow in the glue code to combine and glue these different pieces together. And so that's, I think, an approach where, again, we're applying some programmatic reasoning, but on top of this core technology of reasoning about chunks of a web page. So that's, I think, how this work could be extended in the direction of dynamic web pages. Now, there's other kinds of extension that I think are going to be valuable. There are other platforms that have GUI frameworks. Android, iOS have similar concerns about accessibility, usability, attractiveness, design. And so the tools we've developed could be passed over to those systems. One benefit there is that those systems are saner than the web, which really includes some crazy stuff in it. And so those tools could potentially be faster or maybe easier to use. And finally, the thing I'd like to look at is trying to get this in the hands of actual designers. We've got some projects starting up. We're hoping to work with some folks at Adobe and Instructure, both of whom are in Utah, and try to get some of their designers to see, can they use verification tools like this? And naturally, there's a lot of questions there. Can designers write specifications? Or how do we help them write specifications? Can they interpret the counterexamples? Can they develop fixes? Or is that something that we should look at applying synthesis to do automated fixes? So that's something I'm hoping to work on as well. Ben?
Seems like one thing you haven't talked at all about is like aesthetics.
Yeah.
Can you encode aesthetics? Obviously, you can learn aesthetics. It seems like a lot of things about once you have the notion of a specification, you can generate it for different purposes.
Yeah, I'll tell you a little dirty secret there, which is the tool works just as well for aesthetic properties as for accessibility ones. But it's harder to pitch people with the idea that aesthetics matters, especially if they work on programming languages. Look, I don't need to spell this out for you. Accessibility is this kind of yes or no thing. I'm not going to use black and white there. It's this kind of yes or no thing. It's binary. Whereas aesthetics, it's more complicated and rich space. Things might be more or less attractive, not attractive or unattractive. And so the idea of specifications seems more natural in that space. But one thing I am interested in is, designers build these fairly rigid frameworks of how things should look. Design guides, palettes, style guides of various sorts. And they might be interested in verifying conformance to these systems because that has value to them for branding purposes, usability purposes, teaching users, and so on. So you're totally right. Design is just as valuable and applicable question here. But to sneak this into the PL community, I've been talking mostly about accessibility. Alex?
Is it feasible to apply this reasoning preemptively as the web page is being written? Something like the CSS you're writing right now has potential to be inaccessible under certain conditions and forget about it?
Yeah, there's actually been a user project last quarter, student project last quarter that tried doing something like this. And I mean, like all student projects, it only sort of came together. But I think that's definitely an exciting direction, right? Definitely questions there about speed. Right. If it's as you write, it really needs to be as you write. You may have noticed that before I talked about scalability, I had a timeout set at 30 minutes. That's not really real time. So working on speeding that up and trying to make use of information we already have from previous iterations of the page. But you're totally right.
But even assuming scalability, there are definitely periods during web page development that are not real time.
Yes.
There is compilation, there is rendering of the actual web browser, and
yes. Yeah. And a lot of these automated tools are run at that point.
Yes, exactly.
Right. So you can imagine trying to roll verification into that step.
I would worry more about incomplete, the semantics of an incomplete CSS.
Yes.
Which changes.
Yes. But I mean, we are using a solver in the back end, so we have some fundamental capability to deal with this. We're talking about the independence of different parts of the page from each other. So that's definitely an interesting direction. Emery?
Yeah, so my question was really about modern web pages. That, certainly they include JavaScript, but really there's this vast family of frameworks, as you know, and some of them do really, really, let's say, creative things with JavaScript and with the page on the fly. So the page is, let's say, extra dynamic.
Very dynamic.
Yeah. So do you see the sort of induction thing that you outlined as being applicable even in those spheres, or do you think that you'll need new techniques?
That's an interesting question. In some sense, you can think of the direction of work I've outlined as kind of chronologically following the web. First there were just static pages, then JavaScript came onto the scene, and there's a real worry that you'll never catch up. I think more broadly, you're totally right. There's a lot of different frameworks. There's a lot of work going on in the JavaScript community. JavaScript programs, despite being just web pages, extend into the millions of lines of code and do all sorts of important things. So one of the broader things that I would like to work on, not just in this project, but in sort of a broader research agenda, is web browsers. Web browsers and the frameworks people build on top of them. There's a lot of interesting software that we haven't applied PL reasoning to at all. And we can, to do performance, to do analysis, to do modularity of various sorts. One challenge people have today is writing large JavaScript programs that are composed of different pieces, but that all operate on this global data structure, the web page. Right? So how do we make that more modular? That's a classic PL design question that we can attack in a lot of ways.
Alex? Following up on this, so with modern frameworks like React, there is a lot of written guidelines and best practices and templates for how exactly to develop components in the framework of React, etc. Is it possible to automate at least some of these and integrate them into React linter?
Yeah, I think so. And one of the things that I'm starting to work on is how do you verify that a page doesn't do too many what are called reflows?
Right.
Basically, there's certain APIs in the browser that cause the browser to do a global whole page relayout. This is a kind of cost analysis, if you want to put this in PL terms. But instead of a cost analysis for like a functional language, which has a lot of these complicated things and loops to deal with, in the browser you have the potential of it being much simpler. The cost of a reflow is much, much higher than any other operation, and basically more than one is bad, right? Because you think of JavaScript as running single-threaded and monopolizing all the computation of the page. So more than one is too many. So there's a possibility of doing a cost analysis there that works for large programs and gives actionable, important feedback, which I think would be really exciting. So that's an example of sort of other analyses that we'd like to do on web pages. Ben?
So going along with the the different uses of specification, so you could also use it for privacy and security, right? So for example, have you thought about looking for elements that are non-visible that could be used as tracking?
Yeah, that's interesting. Or another example of security that we've thought about is there are certain parts of the page that you want to look different from other parts of the page. Like user-generated content should not be able to look like an alert from the system, right? Because that could make you click on links you shouldn't and so on. So that's another example where we have, and that's an interesting specification because it's not about similarity, it's about dissimilarity.
But you could imagine it being a user-facing capability, right? It's like,
yes,
I don't want you to do anything with this web page until the checker checks to make sure that it's not a bad one, right?
Yeah. So I think that's an interesting idea. It's not one we've pushed on too much, but you're right. The same capability could work there.
So nowadays, many websites run advertising, and some people also run ad block software as well. So when the end user see the website, maybe it's very different from what the developers see, right?
Yep.
And so how did your work solve that problem?
Yeah, that's a great question. I'm really happy you brought up advertising, actually. Advertising is really interesting. Not in the direct sense. It's usually really boring. But what I mean is it's actually sort of an adversarial part of a web page. When you design a web page, you don't know who wrote the advertising script, and they might be kind of shady, so you don't trust them. So, for example, this notion of verifying a page modulo some other components that have to maybe satisfy some specification. That's an interesting way to look at a web page that includes certain parts that are going to be used for advertising. That's one direction, for example, that would be interesting to go. And you can imagine taking an advertising script and verifying it against one of these conditions. So you say, well, I'm I'm OK with advertising that satisfies these preconditions. But if you don't have like a proof attached to your advertisement saying it won't break the layout of my page, which does happen, then I don't want to run it. So that's an example of, I don't want to say verified advertising. That sounds like I'm working on the wrong team here. But looking at advertising is an interesting component of web pages. And then, of course, you have all the same security and privacy properties as well, right? Advertising that is off-screen. That's interesting, right? What is it learning about you? You might not know there's an advertisement from some company, but it is, et cetera.
The next question is that, so your tool has verified that some website will work with disabled people or people with some disability, right?
Yeah.
Have you actually tested with real people, or?
Yeah. No is the answer. I mean, we've been working from accessibility guidelines that are validated against a lot of experiments with people with disabilities. But you're right that ultimately this has to be grounded in the actual experience of users. And right now we've been starting from these accessibility guidelines because there's a large body of knowledge there about what kind of accommodations even make sense. Right? If I tell you the text should be big enough, like how big is big? The answer turns out to be 18. But I didn't know that until I looked it up. There is sort of this other aspect here, which though this work touches on accessibility, right, it doesn't do the whole job for you. You still need to understand people with disabilities and their needs, and you need to come up with design approaches that address those. Right? Verifying those approaches, that you've implemented those approaches correctly, is only one part of the problem.
Is there any legal case of disabled people suing a website because they couldn't renew their insurance or something? Is there anything like that?
So I would love to tell you a lot about this because I find it fascinating. The Americans with Disabilities Act is a really unusual piece of legislation, but the short answer to your question is yes. There is a legal requirement, even for private sector websites, Walmart is a famous case, to make their web pages accessible to people with disabilities. And so there's definitely a legal case here for working on this, even if you're unconvinced by the moral case of accommodating people with disabilities. And I think especially in the last couple of years, the legal cases, there's some decisions in California and New York and then Pennsylvania about 3 or 4 years ago that's really set up a precedent for this. So this is becoming more and more of a concern. I have designer friends at Google, and the command to work on accessibility for their user-facing web pages has come down in the last couple of years. And so there's been a lot more work on this. I'll take more questions, but while I still have all of you here, I want to slip in a brief YouTube-style interstitial ad at the end of the talk, which is that if, I find this work really exciting. I'm really looking forward to working on some of the things outlined on the slide and also that I've told you about in person. And if you too are interested and exciting about the future of this work, I invite you to come visit or join the University of Utah. It is located in a beautiful natural environment. It is a great city to live in. And we have a large and growing PL and compilers group. So 7 people in the core group now, and 2 of them are new. So by the time you join, it could be 10, 20, 400. Look, I don't know where things are going, but they're going in a good direction. So drop me a line if you're interested. We would love to have you. And so with that, thank you. I'll take sort of the remaining questions. And if I don't get to you or you want to learn more or contact me, that is the URL. And you can find a link to my webpage off of that. So thank you.
And I'll also add, if you want to chat about this or anything related with Pavel afterwards, he'll be around during this afternoon.
Around this afternoon.
So just come by and chat.
Yeah. All right. Thank you all for coming.
Thank you. Thank you.